Have you ever wondered if objects get heavier or more substantial as they move incredibly fast, approaching the speed of light? The direct answer is a bit nuanced, but the modern scientific consensus is that an object's intrinsic mass, often called its rest mass or invariant mass, does not actually increase with velocity. Instead, what changes is its relativistic momentum and energy. This is a key concept from Albert Einstein's theory of special relativity. The why behind this involves understanding the very fabric of space and time. Special relativity tells us that the speed of light in a vacuum is a universal constant, the same for all observers, no matter how fast they are moving. To keep this constant true, strange things happen to our perceptions of time and distance. As an object speeds up, time for that object slows down relative to a stationary observer, a phenomenon known as time dilation. Simultaneously, its length in the direction of motion appears to contract, which is called length contraction. Early interpretations of special relativity introduced the concept of relativistic mass, suggesting that mass itself would increase as an object gained speed. This idea helped explain why it takes more and more energy to accelerate an object closer to the speed of light. However, modern physics tends to avoid this concept because it can be misleading. It implies that the object is fundamentally changing its internal property, its mass, when it is really the relationship between its energy, momentum, and invariant mass that is evolving with speed. So, how does this information help us? Understanding this distinction allows us to accurately model the behavior of particles in high-energy physics, like those in particle accelerators, such as the Large Hadron Collider. It helps us correctly predict their momentum and the energy required to accelerate them. It also clarifies why nothing with mass can ever reach the speed of light, because it would requiring an infinite amount of energy to accelerate even a tiny amount of invariant mass to that speed. The true utility lies in appreciating that energy and mass are deeply intertwined, as expressed by Einstein's famous equation, E equals mc squared. As an object gains kinetic energy, that energy effectively adds to its total inertia and resistance to further acceleration, but its fundamental, invariant mass stays constant. This deeper understanding provides a clearer and more consistent picture of how motion impacts objects in our universe, particularly at extreme velocities, focusing on how energy and momentum are affected rather than a change in the object's intrinsic substance.